So looking up at the calendar here, first off, I want to make sure this is on, yeah. Looking up at the calendar here, you see that our exam is coming up on the 26th, and it's at night. So where are we here? So we've already started simple regression. Simple regression is the last thing we're going to do before the exam, the last part. And then you'll have a lot of practice exams. You'll have one in your notebook. You have one, I'll give you open one up online. You can take multiple times and so forth. So you're going to have a lot of practice materials. So don't forget to do our bonus survey 2 up here. That's right here. And the homework. So this is unusual, this Wednesday, Friday. It's because we're just having an unusual week. So you have homework tomorrow, and a lot of you have already started that. Now, so what we do today, you'll be at the end of today, you'll be able to do both these homeworks, and I'll post this. Any questions about anything that's upcoming? If you want, I'm going to have people are asking about conflict exams. People online want to know where to take the exams. Everyone is going to take the exams here on campus, unless you can't, unless you're off campus somewhere, and you can't get to campus. This is for the online people. Then you take it through ProctorU. But everyone else online and in person will be taking them on campus, and it's in a bunch of different rooms. And as soon as you sign up for the conflict, which is going to be due right here, I haven't posted it yet, and anybody who wants to can sign up for the conflict, and when is the conflict? It's 4 to 8:30 the same day. All right? So you can just do it just because you want to, because you think better in the afternoon. It's up to you. I want to give you some flexibility. All right? Any questions on the exams? And you get to bring any calculator you want, and the example in your notebook, the sample exam on the yellow pages, is the exact exam I gave last semester. So you can get a good feel for what it's going to look like. Of course, it's going to be different, but you'll see the type of problems that are being asked, and you'll have an hour and a half. Okay? Any questions on that? Now, homework. A lot of people are having trouble with confounders. They're confusing. So I saw a bunch of questions on here. So if you did have questions, these were not so easy, especially one of them I even said was confusing in question 4. Right here, I said, this question is confusing. I wrote it, and then I realized it's confusing. And I said, I'll send you a note explaining why. Until then, just answer either way. You can't get it wrong. And I just, basically, it doesn't matter. If you said correct, if you said incorrect, it really was not. These things are really hard, these confounders, and I just gave you one that was a little bit above what I've talked about. So you can go down here and you can read it. Like, people ask questions all about these, and I've explained this. So if you haven't, look down here if you're confused at all, and you'll see my explanations. And because a lot of people are confused, but I don't want to spend time now because a lot of you got it right. So just look here, and hopefully that will answer your question. All right. So anything else before we begin? Okay. So where we left off, let's just remember where we left off. We were looking at page 30 here, and we were just talking about the difference between these two lines, the SD line and the regression line. And then we looked at what the formula for the slope and why it's true, and then we talked about this error, the standard deviations of the errors around the residuals around this regression line. So we talked about the regression line right here as the least squares line, right? That's how most of you who haven't, that's probably the only way most of you know it if you haven't been in Stat 100. But there's another really intuitive way that might help you. So it certainly is the line, as I say up here, that minimizes the sum of the squared errors, residuals, right? But there's another nice way to look at it, and maybe I can show you with the data set that we're going to be looking at on the next page. And this is a data set that has the exam scores and final exam scores of a group of Stat 100 students a long time ago when there weren't that many people in Stat 100 when I first started teaching it. So, and you can see these are really what the Stat 100 scores were back then this is the semester before I started teaching it. All right, so just looking at this, you see these two lines, and one of them, which one do you know? Which one would be the SD line? It's the one that's always steeper. So this is the SD line right here. And this one right here is what we call the regression line. Okay? So now I'll make this dashed. And this line would be what? The SD line is the line of equal SD means equal standard deviations away from the average for both your x and your y variable. And remember, these two lines cross at the point of averages. So that's when the x right here, we're predicting final exam scores y from x. And so this would be the point 83. Does it look like 83? Yeah, it looks like about 83. And 73.6. Yeah, that looks about right, and that's the point of averages. And what this SD line says is that if you went over one, that this is the line where everybody has the same z-scores. So if there was a perfect prediction, if I could perfectly predict your final from your exams, everybody would be on this line. Some people are on this line. And the people who are on this line, like this person right here, that person has the exact same z-score in x and y. It means, like, if, for example, if you had a z-score of 1, 1, it would mean if you went over from this point of average, 9.2, added not, you'd have a z-score of 1 standard, and then if you went up 10.3, that person would have a z-score of 1, 1, and they'd be on the line. So that is the idea, but this is a real data set, and I think I want to show you in this line right here, which is the regression line, minimizes the sum of these squared errors, which is going to be, which is the way that this line is calculated. But another way that is a very intuitive way to see it is, I'll show you in the real data set. Okay, and then we can draw it on here. But let's go to we loaded this up, and let's look, and you can find this and find it yourself if you go to our data program and choose a data set, and it's called the grades. So we're going to be looking at this a lot, so you might want to glance at it yourself and find it on here. It's called the grades. Okay, under T. So now we've what? This doesn't. Oh, this is the percentages that this says that the homework, we had a different way of grading. This meant that there was in-class homework we did in class. We had small classes, and it was 8% of your grade, your final. So this is the grade distribution at the time. But what we want to look at is the scatter plot, okay? And we're trying to predict how people's on the x variable, how their exam average, their midterm exams, correlates with their final, how well it predicts it. And this is the same exact data set you have in your notebooks. And so how did this regression line right here, how do we arrive at that? So a very intuitive way to think of it is by drawing something called a regressogram here. And you can make as many of these, let's see, of these bins as you want. So for example, let's make it look a little better. Okay, so what the idea is that you can think of the regression line, this line, as a line that comes as close as possible to predicting the average y for each x. So for example, before I even draw that in the regression line, let's look here. So for somebody who got this exam score, there's only one person who got a 50-something. Well, the average in that vertical strip, there's just 1 point, so that's little horizontal line represents the average y for everybody who got that x. Let's do a better one. Like here's one where 1, 2, let's look at these 3 people. They all got about a 70. And so this little horizontal line is the average, not the median, but the average of those 3 points. Let's see. So maybe we can make it better so you can see where there's just, okay. Do you understand what this is doing? Like there's 2 people within this, so the average is right there. And what we'd like to do, another way of thinking of the least squares line, is the best fitting line through all those little horizontal strips. Because what we do when we predict your final score from your exam score is we look at all the people who scored. For example, here's all the people who scored 90. And the regression line is an estimate for the average final score for all the people who scored 90 on the exams. So that's another way to think of it, the regression, how you arrive at the regression line. If all these little horizontal strips formed a line, well, then it would be the line, obviously it would be the regression line, would be the line right through them all. But they don't, so we're trying to get the best fit through there because we want to estimate the average final score for the people with any particular x, value. Do you have any questions? Does that make sense? Not if it makes sense to you. Okay, so that's the idea. Maybe we'll draw it. Let's draw it. Let's get rid of this for now. Now, let's just get rid of this. So that's the regression line. Now, what is the SD line? You see, it's steeper. It's going to go through the point of averages. You can look at the stats here. And I rounded the stats, so in your paper, on your notebook, it has an exam average of 83. Here it's 82.89. So we're not going to get exactly the same, it's not exactly the same statistics because I want to do it really quickly, so I rounded everything in so we can do it in class. But you see there's the point of averages where the 2 lines cross. And when there's a perfect correlation, which, for example, a perfect correlation between, between what? Exams and exams would be a perfect correlation. You see, then everybody's on both lines. But that's the only time that the 2 lines would be the same. With anything else, you're going to have a less steep line. If there was no correlation, like exams predicting what? What would be no correlation here? Exams predicting maybe like, what? Your gender predicting your, exams predicting gender. So what is this? This is like, I guess there was some correlation there. But, and it's a negative correlation because females were coded as 1s or something and they did worse on the exams. But this would be, there's still a very, very slight correlation, like this SD line. So this is our best estimate, right? And if we did the regressogram, all it's doing is looking at the percentage of females for every exam score. And it's pretty shallow. The correlation coefficient is almost 0. I can't get a 0 correlation coefficient here, but anyway, that's the idea. Okay, so you guys, I really encourage you to play around with that. It's real data, it's a lot of fun, and you can understand stuff that way. So let's go back to our notes, and let's get going and work on this really. This is a page straight out of Stat 100, so Stat 100 people are going to feel very at home here. So let's look at this. So we want to find the slope and the y-intercept of the regression equation for predicting finals from exams. We're predicting, whatever you're predicting, that's the dependent variable, think of it, and that's your y variable, and your predictor variable is the x, the independent. So you might want to do that here. This is our x, and that's our y. Okay, now, find the slope. Well, do you remember what the slope is? It makes sense that the slope is, think of the slope. Of course, the slope is r And it would just be r if you didn't have to worry about the standard deviations. But remember, this is all, they have different standard deviations here. So it's r times the standard deviation of what over what? Which one over which one? Well, think rise over run, y over x. Okay? Like, whoa, she stopped. Let's just like party. Okay, so now here we are back, and people hopefully, now everybody can hear me again. Okay, so we're calculating the slope here, and so we say 0.6 times the ratio of the standard deviation. So we're up here, and we say either the ratio, what is it? It's y over x. So it's going to be 10.3 over 9.2. Right? It's how far you go over in the x direction, and how high you go up, okay, in the y direction. All right, so we'll do that, and we get, when I did that, 0.67. So that is our slope for the regression line right here. We're figuring out this slope. Okay, and now what do we want to do? Now we want to find the y-intercept, so what should we put in there? Well, this equation is true of predict every point on the line. We have this point right here. It goes through the point of averages. That's the only point we know for sure that's on that line. So we'll plug in average for 83 for, we'll plug in 83, put an 83 in there, and then we'll put a 73.6 here and just solve for the y-intercept, right? So let's do that. So we'll have 73.6, that's our final, equals 0.67 times 83, right? We're just plugging in that point of averages, plus our y-intercept. And now we're just going to solve for the y-intercept. And I did that, and I got 17.99, and we'll round to 18 and put that in here. Okay. So the interpretation of that is that for each additional point that students get on their exams, that they have on their exams, our best prediction for their final, on the average, their final increases by 0.67, by 2/3 of a point. And this y-intercept would be people who get a 0. It doesn't really make sense. People who get a 0 on all their exams, well, I guess there have been people who our best prediction is an 18 on the final. All right, so then we're going to use the above regression to predict the exam score of a student with an exam average of 90. Okay, so let's just take a quick visual of what we're doing here, and then we'll use this equation to make the prediction. So we look at the people who have an average of 90. So they're right here. This is what we were doing before. And we're saying, okay, so what we're trying to do, remember, within this vertical strip here, well, these are all the people who got about a 90, that our best estimate, this is estimating the average of those people. And if we went straight across here, we should get something, our y value, our final value should be something in the high 70s. But we can't tell exactly until we use this formula. So let's do that. So what we're saying is we're doing the predicted y variable, the predicted final. We're going to start putting a little hat over that. That means predicted is going to, because that's just what we're predicting, is going to be 0.67 times the exam. So in this case, the exam's average is 90 for these people, plus 18. So that's 78.3. So that's what this little point turns out to be. We knew it was the high 70s, But until we did it, we couldn't. We just eyeballed it. We couldn't tell for sure. And now we know that that point right there that corresponds to an x value of 90. This point right here is 90 for people 90 78.3. 78.3. Okay, so we've got that down. And now, any questions so far? Okay, so now what are we doing here? Do you think that prediction will be exactly correct for all the people? No, look, you can see right here, it's not. There's a lot of spread. So now what we want to do is we want to add some wiggle room. We want to say give or take what, right? Basically, we look at these errors up and down, and we want to look at what the typical size of those errors is, which is the standard deviation of the errors. That adds that wiggle room. So we'll use the standard deviation of the errors to do that. Now, we did that last time. On the previous page, we used this formula. We said the standard deviation of the errors depends on what? Two things. Well, one, it's the square root of 1 minus r squared. The smaller, if r is 1 or negative 1, perfect prediction, we have no errors, right? But it's times what? It's in terms of, we're making a prediction for your final score, so it's dependent on the standard deviation here of the finals. What fraction? If we knew nothing, it would be the full standard deviation of the finals. And that's if we had a correlation of 0. It's times s dy. So it makes a lot of sense. And that, in this case, is going to be the square root of 1 minus 0.6 squared times the final standard deviation. Don't get mixed up. We're predicting final. So it's going to be, this is the final score, give or take some points in the final direction. Don't get it mixed up. Okay? So that's times 10.3. And of course, it's always going to be less than 10.3 because the smallest this can be in absolute value is 0, right? That's going to be 0. The smallest when you have no correlation, then you'll get 10.3. Any other squared r is going to reduce that, and it's going to give you some better prediction than if you knew nothing. So in this case, the wiggle room, we do this, is 8.24. So for sure, if you got a number bigger than 10.3, bigger than standard, you made a mistake. So that's the answer there. Any questions so far? All right, and then the next thing we want to do is we just want to, okay, where we're headed towards is building confidence, and we want to put error bars. Statistics is all about estimating the variation. You make a prediction, but the statistics is about saying, yeah, there's variation around that. The error bars, we want to add some wiggle room around that, and that's what this does. So it's just for now, I say attach that wiggle room to your estimate to give your estimate a range instead of just an exact point estimate. Okay, so you always want to give a point estimate, but then you want to give a range. If I told you your final is going to be 78.3, and I said on the dot, that's really different than I said 78.3, give or take 10 points or something. So it's very informative. So here we say 78.3 plus or minus that 8.24. I'm just doing it very informally. And another way to write that would be to subtract, say 78.3, subtract the lower limit would be 8.24, so that would be 70.06. This is to 80 and adding 8.24 to 86.54. That's all I'm doing there. All right, so that's simple enough. And any questions so far? Okay. So now, let's look at the summary. Here, so we're looking at the summary on page 32, and summaries are a good place to start to, when you're reviewing for the exam and so far, it's good to look at the summary page. So let's look at what we need to know here, what you need to know. So I know you're worried about the exam, so you do need to know this. This will not be given to you, but I said this will be given to you. The standard deviation of the errors is also known as the root mean square of the errors. You're going to see that term a lot, mean square error, root mean square error. It's the same thing as the square root of the average of the standard deviations. Okay, so this you'll be relieved to know, even though you memorized this for Stat 100, a lot of people didn't take Stat 100, and I just don't want to give you a brain overload. But I don't think we gave you that in Stat 100, but we're giving it to you now. So this will be provided on the final. I think I mentioned that last time. It's on the cover of the final. So this will be given to you. No, why do I say final? I'm scaring you. I meant exam 1. I keep saying final because we're talking about finals. I mean, this will be given to you on exam 1. That's what I meant. All right, that, but not this one. You have to memorize that one. All right, so now let's see what we want to say here. This R squared, I don't know if our correlation coefficient, first of all, this correlation coefficient, some of you are probably forgetting even how to compute this. And what is this? How do we actually get R? In Stat 100, we spent a lot of time doing that, and in the previous stat courses. But here, why don't I say, if you want to see how it's computed, or remember how it's computed, to see how to compute R, look at the appendix, which is on page 253. Maybe we should take a quick look at it. So much of this challenge is to try to get the same notation for everybody, because you're coming from all different places, so you probably learn things differently depending on what book you used. So let's go to 253, and maybe I can explain this better, because I just realized this isn't clear at all. All right, so let's go to 253, and here's the correlation coefficient. Okay. And I say here it's the average of the product of your z-scores. So if you took all the z-scores of the x, if you translated everybody's exam score and everybody's final score in our example, if you translate it, so each of you would have, instead of having, imagine translating it to a z-score. So your exam scores and the average of your exam scores, whatever you got, translated to a z-score, and then your final score too. And then for every single person in the class, if there are 100 people, you'd have 100 of these products. And then you take the average of them. Okay? And that's the way, that's the Greek letter for R is rho, and that is what it's called. It's in symbols, that's what the population standard, the population R is. Now for this sample, remember that's like when you're this is like, so you're trying to estimate this population with the sample, let's say. Well then, it's the same thing, but people don't usually write it that way. It's really exactly the same thing. I don't need this, I just need a net. It's exactly the same thing, but people don't write it this way. They write it more complicated because, I'll show you how you probably learned it a different way. You probably learned this. It is exactly the same number as this, but you probably learned it like this. 1 over n minus 1, because you're estimating. And then you're saying the sum of the numerator is the same of x sub I minus x bar. So these are the deviations from the average for the x, times the deviation from the averages for the y. This is exactly the same thing, this numerator. But then because people seem just compelled, no matter what the situation is, to use this n minus 1, and they use, instead of using this, they use this. So now they'll put like, they're dividing by n minus 1. See, they do this. This is how you might have learned it. It's a lot more work. Now you do this, but since you don't really need that, and you have to then get rid of it. When you multiply these two together, you get the square root of n times the square root of n. And this will be in the numerator, because that's a fraction. And then the arithmetic means you get back to square one. And this explains the reasoning behind it, why it's like this. So you can read this if you want. I don't want to distract anybody. I just want people come from all different places, and I want to make sure that everybody knows that we're doing exactly the same thing that you learned before. And you can, if you learned it a different way, you can understand it maybe. You can read the reasoning here and talk to me, okay? I don't want to spend too much time on that. But it is the same thing. So let's go back. And now, all right, so where are we? So now, I want to give you a tiny little preview of where we're going, because I think this is sort of the unifying idea of the entire class. All right? And so this idea of the correlation coefficient squared is usually described as the proportion of the variation of the y's predicted by the regression line. And 1 minus r squared is the proportion of the variation of the y's that's left in the scatter around the line. So let me just, because this is a preview of where we're going. So this r squared statistic is featured in all regression analysis. And that's why you're always taught this, because it's such a big deal in all regression analysis. Okay? And the way to think about it is just, so what most regression analysis does, it breaks down the variation, the spread in the y's into two portions, into one that you can think of r squared. The stronger that is, the stronger your signal is. That's your correlation coefficient squared, really. So this is your signal. And then 1 minus r squared, remember? 1 minus r squared, that's our error. That's our noise. So this is the noise. And obviously together, it's a total, together they equal 1 or 100%. That's true of anything. But what are we trying to explain? 100% of what? What we care about is this variation in the y's. We want to predict it. If everybody got the same y, same final, there'd be nothing to predict. So this is what we're interested in, predicting, why some people are so far up above average, why people are so far below. And we're trying to predict that with some line here, right? That would be our model. And this is our signal, if we can get a linear trend here. And then the scatter around that is our error or our noise. So what we're trying to predict here is not just any old thing. It's what statistics is all about, variation. So that's what we're trying to predict, the variance. So let's just say, so what we're doing is just not this. It's really what we're doing is we'll multiply through, and you'll see it's true of anything, but what we care about in statistics is the variance. So we'll just multiply through. So we care about the variance. So multiply there by the variance of the y's, what you're trying to predict, and then the variance of the y's, plus 1 minus r squared times the variance of the y's. All right, and this right here, r squared is the proportion of the variance, we can read it, predicted by the regression line. So this is the strength of our model. In this case, we just have a simple line as our model, but we're going to have really more complicated regression models with more variables, and this is always the strength of our model. And this part right here is the variation left in the errors. It's the strength of our errors. And so what we do is, and in fact, can you see that is like the standard deviation of the errors squared? Look, if you squared this, you get 1 minus little r squared. That's equivalent to 1 minus r squared. And this is just for the simple case. And if you square the standard deviation of the y, you get the variance of the y. So this right here is our root, the square root of the mean square errors. So this is this whole process is called analysis of variance, splitting variance of your y's into two pieces. So that's what we're going to do in the last chapter before the exam. We'll just analyze the same data we analyze another way using something called analysis of variance. And we're going to be using it throughout the entire course. So this is called analysis of variance. Sometimes people abbreviate it ANOVA. And it's just a way, all we're doing is looking at the signal to noise ratio and coming up with some statistic. You know, we're going to split up this variation, and you see how we do it, and we're just going to look at this, how strong the model is compared to our errors. And that's what analysis of variance is. Okay, so now we have to start using, before we do this, we're going to use regression to make predictions. So far, we've just looked at descriptive, right? We haven't done any predictions yet of new data. All right? So we have to basically put error bars around our slope. So linear regression, using regression to make statistical inferences about a wider population. So far in this last chapter, we just looked at as if it was all the students, 100. But what if the 100 students were chosen from wider population, and we want to make predictions about that regression line has to have error bars around it, around the slope. We have to make, so that's what we're going to be doing. Okay, so let's look at it. That's more complicated. We have to make more assumptions. So whoops, yikes. I'm glad I didn't injure anybody. Any questions so far? Oh, sorry. How many people have already, I know we didn't cover this in Stat 100, right? We've already done inferential statistics in regression, looked at how to look at the standard error of the slope and all that. Just raise your hand. Okay. So you'll probably know this already, but hopefully it'll be more intuitive. Okay. So now, so far, we've only used regression descriptively to analyze the relationship between two sets of numbers by drawing the scatterplot and calculating the correlation coefficient and the slope of the regression line. But now we're going to use regression to make inferences about the wider population from what's known about our sample. Just like back in Stat 100, we use sample averages and percents to estimate population averages and percents by computing standard errors and building confidence intervals. Now we'll do the analogous process with our regression statistics. To do this, though, we need these 4 assumptions. Linearity, that means that our data follows a linear trend. Independence of our errors, we saw that was important already in computing the standard errors. To use the square root law, we need to know that the errors are independent. Equal variability, we haven't talked about that. Another word for that maybe people have heard is something called homoscedasticity. Homo meaning same, like homosexual, same, and scedasticity meaning spread. So, and then the last one that really only comes up if you were talking about doing a t-test is normality of the errors. This doesn't enter in until then, so we might not even get it today, but if you want to start doing t-tests on this, or you have to make assumptions about the normality of the errors. Okay, and some people abbreviate this as independent, identically distributed normal errors, and and also that your plot follows a linear pattern. Okay, so we're going to need to start using a little bit more formal notation because it's really confusing if you don't. It gets really, now we kind of need to. And so we're going to use these Greek letters we talked about before for the population parameter that we're trying to estimate, like the slope of, if there was a true population out there, or let's say let's just make it real. Let's say we're drawing from 2,000 students, and we only drew 100 students, so there'd be 2,000 students, huge class, and we're just taking a sample of 100 out of them. So there's a true population parameter. That would be the population slope. And we use Greek letters for that, and we use Roman letters for our sample of 100, the slope for that, okay? And then we put hats on our predicted values. I started doing that. I put a little hat on the final when I said I was predicting it. Okay, So here's our population model, our regression equation. These are Greek letters, the betas, and we start, the convention is to put the y-intercept first. And that's a parameter we're trying to estimate. All the parameters are these betas, and that's beta 0. And this is beta 1 for one slope. We're going to very soon start putting more slopes in. It will be beta 2, beta 3, etc. But now we just have one, we just have simple regression. And what's this epsilon? That's the errors, and these are the assumptions that we make about these errors. This is that they're normal. That's what that n says, with 0 mean. And this standard deviation, the same standard error, equal variability. And that's right here. Okay? And then we have our sample regression equation, and it's used to estimate this. We don't know this. And so we're trying to predict a y, and now we use the Roman letters right here. I'm saying the predicted y equals this. Another way, some people just say y equals this plus this, but then you'd have to add an error term. I'm just saying what the predicted y is. I put a little hat over it. Where y is an observed value of all the y's, the capital Y's, all the y values, and this is an observed value of it, and y hat is a predicted value of y. All right, so let's just get to it now. You'll understand it better when we do an example. So why don't we just do the same example we did before, this example we just finished, and pretend that this example can't, so we don't have to go through this again, all these calculations, and pretend that we randomly drew these people from all, like right now there's 2,000 Stat 100 students. So pretend we randomly drew them from like a much larger class. This, if you can believe it or not, when I first started teaching, was all of Stat 100. But now there's so many Stat 100 students. This was years ago. This was like in the early 80s. So now there's 2,000. Amazing. So pretend we drew this, and of course we wouldn't get these because the averages have gone way up. There's grade inflation. Y'all know that. Plus we're teaching it better. Okay, so that's where we're at. And so let's just look. Suppose the exam averages and final scores, and we're going to be doing an iClicker because I can tell you're getting bored. So we should be doing it, but let's just get some reasoning down, and then we'll do some iClickers sort of closer to the end. Is that okay? Okay, so suppose the exam averages and final scores of the 100 Stat 100 students from the previous example were a random sample from a much larger class of Stat 100, say 2,000. How can we use the sample slope in our regression equation, predicting finals from exams, to estimate this population slope? So we have the same, pretend these are the samples. Okay, we have to set up a probability model like we did before. And you know, there's different ways you can do it. I think the most intuitive is to just have a population scatter plot, right? So let's just say there is this ideal scatter plot out there. So we're going to just have this whole ideal out there. This is the, why do I say ideal or imaginary? Lots of times there isn't a real population, and people are just imagining you're choosing from a larger population. In this case, let's just make it real and say there is a real population, but it's wider. So it's our real population, and it has a population, it has a lot of people in it, 2,000. Let's say all 2,000 students are inside here. This represents all 2,000 students. So this represents all 2,000 students. And there is some scatter plot here. You know, exams for all 2,000, you know, finals. This is just their exam. We're just plotting their exam and final scores, their exam average, midterms, and finals. And we think that there's this positive correlation. We don't know what it looks like. And we think that there's this regression line. We know there's a regression line. We just don't know what it is. It's because we can't sample all 2,000. Let's say I don't know. Let's say you're a student and you don't have access to this data, so you take a sample of 100 from it. And so there is some ideal beta 1. That's our slope. We just don't know it. And that's what we're trying to estimate. So that's the point. So we do that, and we randomly, let's say you guys wanted to see what the correlation was, and you didn't have access to all this, so you randomly draw what? N equals 100 of these people, points. And it's without replacement, obviously, because you want to get different people. This 100 is not going to make a big deal, but if you want it to be, If you wanted to, you could use something called a correction factor because it's without replacement. But it doesn't matter because 100 is a very small percentage of the 2,000. So it's not going, every time you take point, if you took all the points out, you'd have no variability. So every time you take points out, obviously your standard error goes down by a certain factor. But we're going to ignore that. And we'd get a sample scatter plot, right? And every time it's different, right? Every time it's going to be different because you're sampling different people. And we'd get a sample scatter plot. And I don't want to draw it because we have it just right. We just did it. And we'll put it on the next page. Do I put it on the, yeah. Okay, here it is again. This is it. It's right there. Okay, so see next page or previous page. It's the same thing. Get a sample scatter plot shown on next page. Okay, so we've got that. That's the idea. And the idea is that, okay, so this is the one we got, but we're going to get a different 100 people each time. We'll throw those back in, do it again, do it again. And what we're trying to figure out is how much variation there is. How much variation? Think about it. If the true population percentage was, or if the true scatter plot, just to give you a, make it dramatic, pretend it was like this, and there was a perfect correlation. And there's 2,000 of these people right on the line, then if you, no matter what 100 you choose, you're not going to have any variation. You have a perfect, you're going to get exactly the same thing, right? And if there's like no correlation, well, you could get a perfect, if you took like 3 points. If you took 2 points, you would get a perfect correlation. If you took, you'd get a perfect, you'd get, you know, no, you'd have nowhere, no, you'd have a slope of r equals 1 or -1. If you just took, you have to have more than 2 points, right? But if you took 3 points, you might get very close to that. The more points you take, the more likely you are to get the no correlation because there's a lot of big standard deviation in here. And the more points you take, it's going to be closer to that. So we're just going to be doing exactly the same thing, you know, plotting the distribution of the sample slope. And it follows the same rules as the sample average and the sample percent. It's basically the same idea. Each time you sample, it's going to depend on our sample size. It's going to reduce the variability. And the scatter, or this inside here, the less scatter, the less it's going to vary. So that's what all we're doing. That's it. Okay, so that's, but it's going to, you know, we have to work out, be very careful about our assumptions and so forth. So the first thing we want to do is say linearity. So we're going to go through these assumptions and hopefully you'll understand why they're important. So if they're violated, which they always are, you'll know how much of a difference it's making. So for the first assumption, linearity, what does that mean? Does the plot look like it might well fit with a straight line plus scatter? So let's look at our plot. And it does. That's pretty good. What would be, so we can say yes. So what do we want to, what are we looking for? So let's just think about this and think about what we want here. How can I look at it? Okay, so if we saw it, that's good. So good would be, we want to see something like, you know, a plot like this that has a linear trend, right? That would be good, and ours is good. What would be bad? A bad wouldn't show linearity. It would be a curvy linear plot, for example. What if, I don't know, it looks something like that? That would be weird. The people just who do in the middle on their exams do the best on the final. If they start doing too well on their exams, then they're going to fail the, I mean, something like that. Obviously, why would it be bad? Because we want to fit a different, we don't want to fit a line. We want to fit a curve. So we'll figure out, we'll look at that later. We'll have to do some, what to do if it's not linear. That's going to be a big part of this course. But for now, this is good. So yes, it's good. So we've got that. If the plot looks linear, find the slope and the y-intercept in our sample regression equation. Well, we just did this. So it's a linear plot, so it looks good. So your next step is to then find your sample what I say right here. And we already have that. We just did it, so we don't have to repeat it. What we want to do then is we want to just get, we have to get the beta, the y-intercept in the sample, plus the slope in the sample. And we did. We've already done that. On the previous page. Yay! So we got it. We have the predicted y is equal to 18 plus 0.67 times x. So this is our beta naught, and this is not our beta, our b0 and our b1. All right. Let's turn the page. So, all right. So now the next thing to do. Our sample slope, B1, is the best estimate of the population slope, beta 1. But of course it won't be exact. Of course it won't be exact. This is our best estimate. It's the least squares estimate. But of course it won't be exact, since each time we take a random sample, we'll get a different set of points. So our sample slope will vary. Yes, this is what we're doing. By give or take what amount? How much the sample slope typically varies is called the standard error of the slope. And it follows its own square root law. For small n, we'll have to tweak it. We'll just have to tweak it a little bit, but let's just look at for large n first. Okay, we'll have to just tweak it by that n minus some factor, remember? Okay, so now, if assumptions 2 and 3 hold, and we'll examine them and see why they matter, let's look at the formula first so we can understand what it is. So if the assumptions 2 and 3 below hold, then the standard error of the slope can be calculated as our standard deviation of the errors divided by the square root of n. And then also in the denominator is this SDX. So this formula makes sense, except for this part probably to you. The variability of the slope comes from the random errors of y around the prediction line. Remember, if there was no error, there'd be no variability. Do you remember we just looked at that? Right? If there was no error, there'd be no variability. We just did that. So the bigger the spread is around the regression line, the more variability is. You know, like the more uncertainty there is. If they're just all in a straight line, there's no uncertainty. The more variability inside here. So that's your standard deviation of the errors. The bigger that is, the bigger your standard error of the slope's going to be. It's going to change. Your sample slope's going to change with that. And we also saw it also depends on n. But it's the square root law again. And we've already looked at that many times. It's going to diminish the bigger our sample size. There's going to be less variability. We saw that too. If you just take a few points, you could get anything. You could get a negative correlation. You could take this, this, and this. And then the next time you take 3 points, you're going to have tremendous variability. But if you take lots of points out of here, it's not going to vary so much. It's the same rule that we always use, right? So that explains it, and that's, if we stopped right here, I don't think I'd ever have to give you a foot. This would just be super easy for you. Okay, so why do we put the SDX down here too? Well, this is really easy if you think about it this way. Just because we're describing this variability in terms of y, in terms of the slope, y over x. The slope is change in y per unit of x. Look, you'll see it a lot better if we just, the SD of the errors, remember what that is, let's think about it. It's the square root of 1 minus r squared times the standard deviation of the y's, okay? Now look at this denominator. If I just left it like that, without putting that SDX in, there's something wrong there. There's no y over x. That doesn't make sense as a slope. There's no y over x. It's just because the variability is described in terms of y, and the slope is change in y per unit of x. We need to have that in there. So we need to divide by the standard deviation of x. It's just to make the units work out, really. So now we've got it. All right, and so that is your formula for the standard deviation. I'm going to give it to you. I will give you both this part and this whole part. So you have it, so it's given on the exam. All right, so don't worry about it. It looks like, but it's super easy to remember because of, if you think of it the way I told you. But still, I'm just going to give it to you. There's too much to remember. Maybe so there it is. That's what it's going to look like. So there you have those two, and that's the only thing you'll have. Just so you don't worry about it. Most people know it, but I just put it on there, and that's what you're going to have. Okay, so that, now you understand that. Now, why do these assumptions that you hear about so much, why do they matter? This is super important because if you're taking another class or if you ever do data analysis, these assumptions are going to be violated all the time, unless you get fake data sets. If you look in the real world, they're always violated. So you have to think, okay, where does this assumption relate? At what point in my analysis does this matter? And how much is it affecting my analysis? You can't just like learn it like you do in school, like memorize them and then get fake data sets where they're either blatantly violated or perfectly match up the way I was taught. It sucked. Because then you actually want to analyze data and you don't know what to do in the in-between land, which is always. So I really want you to understand where they come from, and we're going to look at what to do in violations. That will be a big part of this course too later on. But let's first think, so why do we even need these assumptions, right? Why? Well, the independence assumption. So the errors in that true underlying regression model must be mutually independent. This is, I'm sure people talk about this all the time, independence, independence, independence. Well, all these standard error formulas depend on independent errors. We saw that last time, and there's a proof in the back of the book too. They absolutely depend on independent errors. So can we model our data as random draws from a larger population or as a random assignment? Okay, what do you do? How do you check this? So now we're going to be checking something called residual plots, and it should show no grouping. This matters. Why? Because if the points weren't independent, well, our standard error formulas wouldn't even work. But like another way to think about it is if like there's a lot of independent, if there's a lot of clumped, like identical twins, then we really, in effect, don't have as big an N as we thought. But more importantly, it's just because we can't use our standard error formulas without it. All right, so let's write that down. This matters because if the points aren't independent, then we just can't use these standard error formulas that we're going to do. We can't use our standard errors, our standard error formulas that are up there. Okay, so what I want you to do is, okay, so let's just, you're going to be looking in every class, you look at these residual plots. These, not the scatter plots. So maybe we should just take a quick gander at them like right now and go back to our PC. And this is the most boring part of statistics for most people, and you spend a lot of time doing this, so hopefully I won't make it too boring. Let's look at this. Okay, so we go to our scatter plot. So what do we want to do? So here, exams predicting final. Let's just get it. Let's get rid of this. Let's get rid of this. Let's get this. Okay, so we've got this. Now, this is our actual scatter plot, and a lot of times it's easier to see these pattern in the errors to make sure they're normally distributed and so forth. I mean, to make sure they're independent and equal variance by looking at something called the residual plot. So, what is a residual plot? So do you see how what you do, like, do you see how it's kind of easier to see the pattern in these errors? So instead of, this particular residual plot has the same x here, but instead of having your final exam score here, it just measures the distance you are above or below the prediction. So your prediction is so basically it's placing this whole line horizontal here. The average, the way this is calculated, the average of the errors is always 0. So for example, instead of this residual right here, this distance is now represented as a number looking to be about 15. This point had almost no error, and its right has almost no, it says no error. And now this doesn't really have a pattern to it. If they were not independent, you know what you would see? You would see a whole bunch of errors grouped together, like clumped together. So this looks really pretty good. So this is what you want to be looking at. So let's write that down. And I have it in your notebook too. So let's go back to the notebook. Okay. All right. So I can see you're falling asleep. I don't blame you. It's really boring. But it's better if you understand it. Okay? So, I mean, this part is boring for me. But, you know, these assumptions, you're going to hear them all the time. Might as well know why they're important. All right. So we want to check. Let's highlight this. We want to check that, let me write this down. Check that the residual plot, if they're dependent, they're going to be clumps. Check that the residual plot doesn't have these patterns, shows no grouping. Then you think, well, maybe it wasn't an random sample or something. Check that the residual plots, or maybe you have a whole bunch of like identical twins, something like that. Check the residual plot shows no grouping. All right? So the residual, what should I say? Should I say good and bad? Let's see, what should I do? How did I do it before? Yeah. So good would just be, this is good, what we have, like that. I'll make a little plot of it. Let's make a plot like, so you understand what's going on here. So this is your x variable. This is 0 here, and these are your errors. And this will be your x variable. Sometimes people draw it with the y, but let's draw it with the x. So these are the exams along here. And these are your errors, the errors, your residuals, up and down, okay? And now what we want to do is we want something, this is a good one, would be something where it didn't really show much of a pattern. No groupings or anything. So as opposed to a bad one, like an extreme bad one would look something like, still this would be at 0, but then you'd have something like, here's a really extreme bad one, like you'd have all these like little clumps there, and you might have a whole bunch of clumps here, so they average out to 0, but it's like this would be an example where you don't have all these points, you just really have 5 groups or something. That would be bad. Ours looks pretty good here. So that means we can go on. Next assumption, equal variance, also called homo for equal, scatterplot. Do you really need to know that? I could put it here. Homo, and then the spread in Greek, I guess, is scatterplot. Heteroscedasticity means what you don't want to see, unequal. Homoscedasticity is another word for equal variance. All right, so now variability of the errors should be the same across all values of x. Are they? There's fewer of them here. That's because there aren't many people down here who did so terribly. But let me show you the good and the bad here. So the good is the same as before, but the bad would look like this. The bad, and you see this a lot. You'll see it a lot in Stat 100 data, actually. The bad looks like, it's a very classic thing to have it look like this, is you'll have a fan-like pattern. So for example, in a lot of our Stat 100 data, it looks like this, and we really should do some transformation of the variables but we haven't done inferential statistics, so it doesn't matter. It only matters when you're doing the inferential stuff. So we're fine in Stat 100. We didn't use it to make inferences about what, something like that. That's terrible. So bad is a fan-like pattern. And why is it bad? Okay. Because the spread should be the same across the plot. Like, see how the spread is about the same? There aren't very many points, but it's the same across the plot. This is really needed because how much the scatter affects the slope depends upon where along x it occurs. If you have changing y near the mean of x doesn't tilt the slope either way, but changing y out at the extremes pulls the slope up or down. So if you have if you have unequal variance, you don't know, your estimates aren't, you're going to be using the same standard error along the whole curve, and you can't. And it's going to change. You can't trust your slope to make future estimates. So you really have to, if you see something like this, you do what's called a transformation of variables. We're going to be doing this usually take a square root or something to make it nice. And then you can trust your estimates, and then you can transform back. You'll see, it'll be not too bad to do that. All right, so it's very classic. That's why they talk about it so much. Okay, to check the assumptions, you look at either the scatter plot. You can look here. There's nothing magical about the residual plot, but it's just easier because it's just easier to see it here. And you look at your scatter, and the result, do assumptions 1 to 3 appear to be satisfied? If yes, then, if no, you're going to have to do, a lot of this course will be telling you what you have to do, and most other courses spend even more time on that. But if yes, now we can attach our standard error estimate to our slope and give it a range instead of an exact point estimate. Finally, so let's do that. So now what was our standard error? It's given up here. Let's see if we can remember it without even looking up there. So our standard error for this slope was what? The standard deviation of our errors. Let's just remember it that way, because we already computed that, and we can save time. We have it on the previous page. Over the square root of n. SD over the square root of n. And this is where when I had people memorize it, because every one of our formulas is SD over the square root of n, right? They'd forget what? You have to have, that's not going to make sense, because remember, that's not going to be the right units even. You have to put that SDX down there, so don't forget that, but I'm giving it to you. So let's just do it. We already did this on the previous page. We got 8.24 right here. So let's use that. So that's our scatter. It makes sense. That's our scatter, right? And now we're dividing by the square root of our sample size. And we have 100. And now we're multiplying by the standard deviation of x. So we just look back at our data, and x is which one? The standard deviation is 9.2. Okay? So we'll put that down there. And the units will make sense if you had, in this they're both points, but if you had height over weight, it would make sense. And then when I did this, I got approximately 0.09. That is it. So now we can give it a range, the same way with our slope a range. All right, so let's do that. What was our slope? Do you remember? Where is our slope? We have to go back and remember what we did for our slope. And it's right here. It's 0.67. That was our slope, a point estimate. So now we're going to say 0.67 plus or minus 0.09. So in other words, now we're going to build confidence intervals. That's the next thing. We're going to use this to build confidence intervals, and we have just enough time to do that. All right, so what is that? This is actually going to be, let's see the reasoning, this would be like a 68% confidence interval, because it's just like one standard error. So it would go down, if we subtract off 0.09, down to 0.58, all the way up to 0.76. All right. Okay. And before you go, remind me, we got to do some, just say you were here, some, if we have time to do a eye clicker. All right. So now here we are. We can do one maybe right now somehow. How confident are we now? Confidence intervals, this is just like Stat 100, like everything you've had before. How confident are we that our estimate will capture the true population slope. How sure are we that if we actually calculated the true slope for all 2,000 points, we'd get a slope within those limits? And now, here's our beautiful normal curve, because of the central limit theorem says that we can answer that question because we know when n is large enough, the probability histogram for the sample slope follows the normal curve because of the central limit theorem. Since the errors in the slope come from the sum of independent errors, we haven't used normality. By the way, that's not even going to feature in until we refine it, until we talk about the t-distribution. That's the only time you need that assumption in normality. You don't otherwise. So if you have a big sample size, the reasoning, that's where that comes in. So it's really important to know where when you're doing this stuff, because when a violation of it comes up, you have to figure out what to do and where it's coming in. So the central limit theorem, if your sample size is large enough, will assure this, will give you this normality. So we know what's the idea. This is the idea of all statistics, all this stuff. If we took thousands and thousands of random samples, each of n equals 100, each one of n equals 100, from the population of the 2,000, we did it over and over and over and over and over again, each time recording a slope, what would we get? What would be the sampling distribution of our sample slopes? Well, they would follow the normal curve. So here's our sample slope. We'll call it B1. And here it is as a z-score. It would be 0, but as a z-score, but as a slope, it is going to be what? If we're this will be the true. We're estimating the true. This is the beta 1, right? That would be right in the middle, beta 1. And then this is the distribution of our sample slope. And the standard error tells us how far we are here. So if we know if we took thousands of random samples and computed the slope for each one, about 68% of the time, it'd be within -1 and 1 of the true population slope, beta. They'd fall inside here. And about 95% of the time, between -2, I'm just estimating, it's really 1.96, about 95% of the time, they'd be within about 2 standard errors of the true population slope, right? So we can be about 68% sure that our sample is within 1 standard error, and about 95% that it's within 2 standard errors. We only see 1 sample, but we can be about 95%. 95% of the time it would land in here. So if we see 1, 95% of the time it would be in there. That's what we're 95% confident that it landed within the true population, within this confidence interval. That's what it means. All right. So now, use the normal table. Let's just do this one. Find a 90% and 95% confidence interval for the population slope. How are we going to do that? Well, a 95% confidence interval is equal to the sample slope that we got, which is that 0.67, right? Plus or minus this critical value that corresponds to the 95%, this z right here. We are looking for the z. I'll just put a blank here. Where 95% is in the middle. That's what it means. That's why we're looking for what z goes right in there. What should it be? 2. Right? That's what it means. That's why this table at the back is so nice, because mostly you do confidence intervals, and it gets very intuitive. You look for 95%, and it's about 1.96, but at least you understand what's going on. All right? Times what? Times the standard error. That's like this right here. I'm just doing that. Z is the critical value corresponding to the confidence interval. That's what it is. The critical value, we've done this many times, when alpha equal, this is an easier one. With confidence intervals, it's so easy. It's just the middle area. 95% middle error is 90, it's 2. Times our standard error, which we said was 0.09. So when we do that, it goes, we're 95% sure that it will be between 0.49 to 0.85. And for a 90% confidence interval, we do the same thing. We'd say this plus or minus, this part is all the same. But now instead of 95% in the middle, we want 90 in the middle. So we go 90 in the middle and about 1.65. And we do the same thing. And then you would get these limits. And now let's just do an iClicker. Why don't we just do this question right here? And that way we don't lose any time. All right, so you can read the question in the book and just think about which of the following, this is an all, you'll get credit no matter but this will be on your, this is important to look at. So I'm just going to start the iClickers and just say if it's A, B, or C. All right, and so you can get out of here soon. All right, so we'll just, this goes down, and all I want you to do is, okay, it's A here. So let's just say, is it A, B, or C? Which of the following statements is true? A 95% confidence interval for the slope of the regression equation predicting. We know they're all the same. We already calculated that. So these are all right. It's just what does it refer to? Well, when you sample, this says for all females. Oh, it's in your notebook. I'm sorry. It's in your notebook. Let's go back to this so people on. Why don't you just vote A, B, or C, and then we'll look back at it, okay? Has everybody done it? Has everybody voted? You can vote D, that you're like completely confused and have no idea what the answer is, because that would be, that's all I want to know. So definitely, if you have no idea what that answer is and you just want to get out of here, go ahead. Or even if you thought about it, you don't know what the answer is, because I need to know that. So D, I have no idea. All right, and so let's stop it. So everybody needs to vote. You're going to get credit? Great. And let me show you the right answer. C was the right answer. Guys at home, I apologize, but this answer is right. You guys did amazing. I can't believe you just